Okay, so now we will one special notation. So if omega in Rn is an open set and with Lebesgue measure, so this is the usual standard measure that we have on Rn and its subsets, then Lp of mu we will write as Lp of omega. Okay, because we understand, we don't have to specify the measure, we know the measure is the Lebesgue measure, we want to know what set we are working on, and so we put the space Lp of omega. Similarly, if you are working with R with Lebesgue measure and you have AB is an interval where minus infinity less than or equal to A less than B less than or equal to plus infinity, it could be infinite intervals also, then Lp of mu, so mu is Lebesgue measure, okay, Lp of mu I will write Lp of AB. Okay, so this is just notation, especially when you are dealing with R or Rn. Okay, so now let us look at some examples, familiar examples. Okay, so now we take X is the set 1, 2 up to n. S is the power set of X, that means all subsets. Okay, and mu is the counting measure. That means mu of A is equal to the number of elements in A, and it will be infinite if A is an infinite set. Then what is integration with respect to mu? Is just summation. Okay, so it is just integration of a function. A function on X is nothing but a set of numbers 1, 2 up to n, so it's a n tuple, and if you integration is nothing but adding the values. Okay, so that is the integration with respect to the counting measure. So every measurable function, every function is measurable because we have taken all sets in the sigma algebra, is identified with the n tuple a1, a2, an, ai in R. So therefore in this case Lp of mu is nothing but our familiar LNP, namely Rn with norm P, which we have defined here. So norm P of A nor X equals x1, x2, xn is nothing but sigma mod xi power P I equals 1 to n whole power 1 by P. Okay, so this is, and it's max and no, so norm xp, norm x infinity equals max mod xi. So the finite dimensional spaces which we have seen are precisely LP spaces. Okay, so next example, X is the set of natural numbers, and again S equals the power set of X, all subsets, and mu is again the counting measure. So now you can immediately relate to what I am going to say. So Lp of mu is nothing but little lp, because a measurable function is nothing but a sequence of numbers, real numbers. So f from x to r means it's a sequence f of 1, f of 2, etc. So it's nothing but a sequence, and integration with respect to counting measure is nothing but a summation, and therefore Lp of mu is nothing but little lp. So in both these cases, only set of measure 0 is the empty set. No other set has measure 0. Therefore, equality almost everywhere is the same as saying equality everywhere. So equivalence classes are singletons. So there is no real fuss. So we don't, this time we are really talking of functions only. We don't have any this. Okay, so now proposition. So let x s mu be a finite measure space. That means mu x is finite. Okay, then LP of mu is continuously embedded in LQ of mu. That means this subset, this notation means it's a subset, and the inclusion map is a continuous linear map. Okay, with whenever you have 1 less than or equal to q less than or equal to p. So when p is bigger than q in a finite measure space, LP, the bigger p, is always contained in the smaller LQ. Okay, so proof. Okay, so trivial if p is infinity, because you have mod f q is nothing but less than or equal to norm f infinity power q into integral over x d mu, which is equal to norm f infinity times mu x, which is finite, and therefore you have norm f q is less than or equal to power q is less than or equal to mu x power 1 by q into norm f infinity, and therefore this shows that the inclusion map is a continuous linear operator map, and of course that L infinity is contained in every LQ. So now let us prove it for any, so 1 less than or equal to q less than p, which is strictly less than infinity. Okay, so f is in LP mu. Okay, so now we apply, so mod f to the q d mu. I am going to calculate, see if this is a finite quantity. So I am going to apply this Helder's inequality to this, with the first function is mod f to the q, the second function is 1. Okay, so if I apply that, so I will get this is less than or equal to, okay, and since q is less than p, p by q is bigger than 1. Okay, so we can apply Helder's inequality with the p by q as the index. So it's less than integral over x mod f to the q power p by q whole power q by p into integral over x d mu. 1 is to the power, I don't care what it is, it's 1 minus q by p. Okay, now this is nothing but mod f to the p whole power q by p. Mod f to the p 1 by p is nothing but norm fp, so this is norm fp norm fp to the power q into mu x 1 minus q by p. Okay, so we have norm fq, that means I have to take the qth root, is less than equal to mu x to the power of 1 by q minus 1 by p times norm fp, and that is finite, and also this shows that the inclusion map is a continuous linear operator. Okay, so now some other examples. No such inclusion in infinite measure spaces. So you have 1 by n, the sequence, 1 half, 1 by 3, etc. belongs to little l2 because sigma 1 by n square is finite. That's pi squared by 6, we have already seen. Okay, so 1 by n. But 1 by n is not in L1 because sigma 1 by n is divergent. Okay, so if something is in L2 doesn't imply it's in L1 if you have an infinite dimensional space. Example again. Okay, no information on reverse inclusions. Even in finite measures, even in finite measure spaces. So you have that, take the function 1 by root x. This is integrable because if you can, what is the integral of 0 to 1 of 1 by root x? This is a non-negative function, so I don't have to take the modulus. So this is nothing but 2 root x eval, so this is equal to 2. Okay, so this is finite. So f belongs to L1. Okay, but f square does not belong to L1, that is integral 1 by x dx 0 to 1 is plus infinity, and therefore you have f is not in L2. F square is not integrable, so f is not in L2. So you don't have any reverse inclusion. L1 does not imply, small LP does not imply big LP. However, example again, let 1 less than equal to p less than q less than equal to infinity. Okay, then little lp is continuously embedded in little lq. So you do have the reverse inclusion in the little lp case alone. In finite, though this is there's nothing can be said. Okay, it's completely free. There's no method by which you can estimate these things. So it happens sometimes, it won't happen sometimes. So even in finite measure space you don't have the reverse inclusions, namely small LP does not belong to a bigger LP, but in this infinite measure space LP and LQ you do have this thing. And not only that, you have that norm x in LQ, the bigger one, is less than norm x in LP for all x in LP. Okay. Okay, proof. So let us take q equals infinity. Okay, so x in LP implies x is bounded because sigma mod x power xi power p is convergent. That means a convergent series, the terms are all bounded, and therefore x belongs to L infinity. Okay, and norm x mod xi for any I is less than or equal to sigma mod xi power p whole power 1 by p, which is equal to norm xp. And therefore if you take the soup, you get norm x infinity is less than or equal to norm xp. Okay, sigma j equals 1 to infinity mod xj, because there is only one term in this thing, and therefore it is, you have this. So now let us assume 1 less than or equal to p, strictly less than q, less than infinity. Okay, so again sigma x in LP, so sigma mod xi power p is convergent, so this means that xi goes to 0. Therefore, there exists an n such that for all I bigger than or equal to n, you have mod xi less than or equal to 1. So, mod xi power q, if I is bigger than or equal to n, is equal to mod xi power p mod xi to the q by p. Okay, I am just writing. And since xi is less than or equal to 1, so this is less than mod xi power p. Okay, so sigma I equals 1 n to infinity mod xi power q is less than or equal to sigma I equals n to infinity mod xi power p, that is less than the full series, so that is less than, strictly less than plus infinity, and therefore this implies sigma I equals 1 to infinity mod xi power q, after all you are only adding a finite number of terms, is less than plus infinity, and therefore you have that LP is a subset of LQ. Okay. So now for the inequality, so assume norm xp equal to 1. So this is sigma mod xi power p, I equals 1 to infinity equal to 1. So this implies that xi is less than or equal to 1 mod xi for all I. Okay. So sigma mod xi equals 1 to infinity mod xi to the q is equal to sigma mod xi to the p into sigma mod xi, into mod xi to the q minus p. This is all less than or equal to 1, so this is less than or equal to sigma, so this is I equals 1 to infinity, I equals 1 to infinity mod xi power p, and that's equal to 1. Okay, so you have, this is true. So now given any x, you take x by, which is not 0 obviously, x by norm xp, its norm is 1, and therefore by whatever we get, therefore that norm xq, okay, so this implies that norm xq is also less than or equal to 1. So norm q of this is less than or equal to 1, that is norm xq is less than or equal to norm xp. Okay, so this proves, so these are some set of examples which we have. So now we will look at some further properties, important ones about LP spaces in this